Innovation is characterized by new functionality added to systems. The means for innovation in all industries is by adding software to the application on existing or new hardware. Oftentimes additional functionality exists in an isolated system and can be integrated as separate workload to your application. As an example, think about motion control added to a system that only provided PLC functionality so far. Sometimes the software for additional functionality can be integrated into existing hardware. Sometimes additional functionality requires additional computers with respective software, and this new computers need to be integrated into the application system. Therefore, scalability is mandatory for innovation. Intime is a platform providing a flexible framework for transparent scalability and integration of workloads. An application thoroughly designed for Intime can scale to any number of computers and coexist with any number of other applications/workloads, without the need to recompile or re-engineer the application. There are a few key aspects the designer of an application should consider. A good design with careful balance of the aspects mentioned will result in easy integration and scaling of the application. Scaling will support consolidation of workloads into one big system as well as distribution of workloads across several smaller systems. There are Intime wizards available for Microsoft Visual Studio to create frameworks designed to implement the architecture of the real-time application. Based on the framework created, the developer immediately can add his application logic to the generated source skeletons. Some applications are designed to get ported to various operating systems, including simple multithreading executives that do not support any memory protection. Such applications are vulnerable to all sorts of issues introduced by unintended use of memory owned by other blocks of the system. Intime process model supports memory protection of the x86 and x64 CPUs implemented by rings, the MMU and paging unit. Mapping such applications to Intime well-bounded processes will ease diagnostics during integration of blocks into a system and also during deployment of the system in the field, because many memory access-related issues get trapped by the CPU. If memory is found being changed unintendedly, who is easy to answer? Always your current process. No code outside this process has access. The question of how or when is still hard enough to answer, but eased because you know the problem is in your process code, and not in other processes. Shared memory is the fastest means of sharing data between processes and a common source of trouble because use of shared memory is completely ruled by custom software designs. Examples of such trouble: the layout of the memory may change and some of the processes using it may not have changed. Semaphores coordinating read/write operations may not be used as intended, etc. Beside the guard pages inserted by Intime Memory Manager to physically prevent access beyond areas inside of the shared memory, there is little help to trap violations of rules that are completely designed by the software architects. Because a process can be loaded and executed on any Intime node, given that the required I/O is available on that node, developers are free to experiment with different hosts and mapping of nodes to hosts. No need to recompile or link the application, just load and go. A system design requires lots of trade-offs. When we decide how to implement the API to required functions, we need to balance execution speed requirements versus easy scalability. The fastest execution time is accomplished by use of the language semantics. Just call the method/function you need. To meet tight time constraints, this may be the only option on a given CPU. Shared library technology may remove the need for individual copies per used method/function and avoid relinking. However, it adds complexity in terms of configuration management to harmonize the version of the shared lib with the application. Implementing the API by the use of IPC gives more options in terms of scaling at the cost of additional runtime compared to a direct call. An example for scaling made possible via IPC: separate inner control loop from log functions. Create a server process to log data received at a data mailbox. The hot part of your control loop would periodically sample I/O, apply the control algorithm on the input, generate output to the I/O and finally send a log message for diagnostics to the data mailbox of the server process. Initially there may be enough time to run the log server on the same node as the control loop driving its special I/O. Should your control algorithm get more complex and use more time, or you need a faster cycle time, the node may run out of cycles to execute the log server on this node. In such situations, you can load the server process on another node. Your inner loop can use more cycles on the existing node with the I/O. By using a data mailbox you do not need to change your control loop. In-time global object technology allows transparent access to IPC objects regardless of which node they are implemented. The delay imposed by IPC to global objects depends how close the server is to the client and how fast it runs. Client and server running on one node see less delay compared to running on different nodes on one host, or even running on different hosts connected by an Ethernet cable. If your system is time-triggered, characterized by precise periodic time intervals, and you exactly know the execution time of your interlocked control loops, thread priorities provide managed execution of your application with minimal overhead. Solely relying on priorities requires a deep understanding of the time constraints. If parts of your application need more time to execute, the implicit, time-bound synchronization between time-critical loops may no longer work. Working applications even may fail on faster CPUs, if the loops are not connected to periodic time intervals but just start. If the higher priority loop has done, the system may get out of sync by producing output too early. If your system is event-triggered, characterized by external triggers that happen at unpredictable time, an explicit synchronization using IPC to control data and control flow is recommended. IPC imposes some overhead, but you benefit from a system that easily scales and works through the different functions in a sequence that will not change, no matter how many nodes you use or how fast they are.